All right, let's dive right in. We're going to take a look at some scientific charts that I know look incredibly complex. They can seem pretty intimidating at first, but stick with me because by the end of this, you're going to see them in a whole new light.
So let's start with the puzzle itself. Take a look at this thing. You've got all these lines, these dots, these weird labels. It honestly looks like some kind of secret code from the subatomic world. But what if I told you it's not a code? It's a contest, a showdown between different ideas about how the universe actually works at its most fundamental level. So, to crack this puzzle and see who's actually winning this contest, we need to get to know the main tool scientists use. It's how they peek into that invisible world of particles, a place we can never, ever see with our own eyes. I mean, that's the whole problem, right? You can't just watch a neutrino bump into an atom. It's impossible. So physicists do the next best thing. They build a simulation. You can think of it like a super advanced physics engine in a video game. But instead of figuring out how a character jumps, this thing is trying to predict the basic interactions that shape our entire reality. And that amazing physics engine has a name, GENIE. Now, it stands for something pretty long, generates events for neutrino interaction experiments, but all you really need to know is that it's the master simulator for this corner of physics. But what does this physics engine actually do? Well, GENIE is the go-to tool for scientists to generate predictions. So before they spend millions of dollars running some massive experiment, they fire up GENIE. It takes everything we know about the laws of physics and just plays out a scenario, billions of times, to create a forecast of what scientists should see when the real particles get going.
It's a pretty straightforward process, actually. First, scientists tell it what's supposed to collide. Let's say a neutrino hitting an argon atom. Then, GENIE gets to work simulating that one event over and over and over again, exploring every single way it could possibly play out. And finally, it bundles all those billions of results into one single chart, a prediction chart, the exact kind we saw at the beginning. Okay, this is where it gets really cool. You gotta understand, this isn't settled science, not at all. We're talking about the frontier of physics. And out on the frontier, different explorers have different maps, which of course leads to a clash of ideas. What this means is that different teams of physicists come up with competing theories, they call them models, to describe the very same event. Each model is like a different hypothesis, a different set of rules for how they think these particles behave under some pretty extreme conditions. And you can see this happening right in the source material. This chart here is comparing predictions from a few different models, like the LFG, CFG, and RFG models. See how each one predicts a different outcome for the same interaction? Now, these aren't just random guesses. They're based on really different physical assumptions. The LFG model, for example, kind of treats the nucleus like a cloud of gas, while other models might see it as a much more rigid structure. Each assumption leads to a totally different prediction. You know, a really good way to think about these charts is to see those colored lines as different weather forecasts, but for a subatomic storm. The Valencia model might predict one kind of outcome, while the Sussov 2 model, which is built on different ideas, predicts something else entirely. Each one is a sophisticated, data-backed claim that's basically shouting, hey, I think reality looks like this. So with all these competing predictions, all these different colored lines on a chart, how in the world do you know which one is right? Well, you do what science does best. You test them against the cold, hard facts of the real world. And this slide just perfectly illustrates the heart of the scientific method. The smooth, elegant lines, those are the theories, the predictions that came out of GENIE. But those scattered little dots, the ones with the tiny error bars, that's reality. That's the raw data coming straight from the particle detectors. The contest is officially on. And that's really the whole point. This isn't just about drawing pretty lines on a graph. It's a super rigorous mathematical test to see which model's version of the universe best matches the one we actually live in. The winner is the model's line can thread the needle through the real data most accurately. So let's check out the scorecard for one of these contests, a neutrino hitting an argon nucleus. You can see the Valencia model, right? It predicts this high, sharp peak. But it misses where a lot of the real data actually lands. But then you look at the Sussov 2 model. It's built on a more complex idea, and it predicts a wider, lower peak. And look at that. Its line goes right through the data points. So in this round, Sussov 2 is the clear winner. But okay, let's step back for a second.
Why do scientists spend decades and literally millions of dollars running these simulations and staring at these tiny squiggles on a chart? What's the big picture goal here? Because it's about way more than just finding the best fit line.
Every single time a model like SUXA-V2 proves it's more accurate than an older one, our collective understanding of physics takes a small but crucial step forward. By fine-tuning these models, we get closer and closer to answering some of the biggest questions out there. What is mass? Why is there more matter than antimatter in the universe? What is all this stuff really made of? And these simulations have massive, real-world consequences. We're talking about experiments like the Deep Underground Neutrino Experiment, or DUNE. They rely on these models to even understand their own results. They use these absolutely gigantic detectors filled with 40,000 tons of liquid argon to hunt for the universe's most slippery particles. All that amazing data they collect would just be noise without precise models from Genie to make sense of it all.
So, if we pull it all together, what have we learned? Well, we've seen that these super complex charts aren't just data, they're the battleground for competing ideas. They tell this whole story, from the predictions made by a physics engine like Genie, all the way to the final verdict delivered by reality itself. And that entire process is how we slowly, but surely, uncover the fundamental laws of nature.
The next time you see a chart that looks like this, don't just see complexity. See the contest. See the search. Because every time a model gets a little bit better, our picture of the universe gets a little bit clearer, revealing the rules that govern everything. And it just leaves you wondering, what mysteries are we going to solve next?